All right. Good morning. So welcome to this class, Introduction to AI. So my name is Gilles Loup. I'm a professor at the Montefiore Institute, the Department of Computer Science and Electrical Engineering. So I will teach you this year this introduction to artificial intelligence. And later on, if you like the topic, I will also teach you other classes about deep learning, advanced machine learning, and other topics related to AI. Okay? I'm also a researcher in the field where I do research in deep learning together with my team. Okay? So welcome. Just to get started, I would like just to get a feel about who you are. So can you raise your hand for the students in engineering? Okay, so almost half of them. What about the students in computer science? Okay. Do we have students from the business school this year? Okay, 2, 3, okay. Do we have Erasmus students? Okay, welcome. Do we have other students? Yes, one. What do you do? Phyllis, okay, welcome. So as you see, the crowd will be quite diverse. So I will not assume that much about your previous knowledge. I will just assume that you know or you have a basic understanding of programming. So we'll do project in Python. And you remember a bit of probability and statistics. But don't worry, I will also do plenty of recaps on these topics. Okay? All right, so let's get started. So let's start with maybe the elephant in the room, ChatGPT. Do you know ChatGPT? Can you raise your hand? Who is using ChatGPT? Who is using ChatGPT on a daily basis? Okay, a few of you. Do you know how it works? Anyone? Yes?
It's going to be a lot to say that I know how it works, but last year we had a project in complément informatique. And apparently it's related. So basically it is a ton of text data, and it's figure out the probability of the next word after a given set of words. And from that, the model can choose a word among them using its probability. I guess there's a lot more.
Yeah, there is a lot more to say, but you are right. So ChatGPT is what we call a neural network. It's one kind of a neural network. Neural networks are something we'll cover later on in the course and later on in the master program, but you will understand how it works. And what is a bit amazing about ChatGPT, so I'm quite sure the first time you have used ChatGPT, you were quite impressed by what it can do. And to be honest, as a researcher, I've been quite impressed from the beginning, and I keep being impressed by the quality of the results. And it's even more surprising because when you know how it works, it's surprisingly simple. So it works exactly as your keyboard on your smartphone. When you start typing a word, it suggests the next word for you. Okay, so if you start with a sentence, so tell me what would you recommend for a one-day trip to something, then you see the suggestions. So basically, ChatGPT or neural networks that are used to build ChatGPT interfaces are built on this very simple principle of having some kind of model which is able to guess the next word given the start of a sentence. Okay? So you may wonder, why is that technology so powerful? Because that seems so simple. So why is it that if you can solve this problem, you can implement something as crazy as ChatGPT? It's because to guess properly the next word, while you need some kind of understanding of the previous words that form the sentence, and maybe also of some external knowledge. Okay, so to give you an example, let's say we start with this sentence. In the 60s, Armstrong, and then tell me what could be possible next words. Okay, anyone can make a guess? Landed? Who said that? You? Anyone else? Walked. So why do you pick verbs?
Walked.
Yeah, but why do you pick verbs? Sorry? Yes, but there are. How many words could you put next to these ones? Like all the possible words in the English dictionary, right? So why do you put verbs?
Because we have extended knowledge.
Yes.
on what's happening.
Okay. What else? Any other suggestion?
Is it subject before?
Okay. So what if what I will pick is performed? How would you complete the sentence?
Perfect landing.
An amazing.
So who knows about Neil Armstrong? Who knows about Louis Armstrong? So Louis Armstrong was a musician, a jazz musician, also in the 60s. So let's say we go for this one. What could be possible next words? Yes? Anyone else?
A trumpet show.
Trumpet show, yeah. Yeah.
The first landing on the moon.
You're smart. Okay, what I will pick is another one. Armstrong performed a moonwalk. Okay? How could we continue this sentence? Yes? For the first time in history. Is anyone dancing? Do you know what's a moonwalk? I will not do it. Yes?
On stage.
On stage. It's a good one. Let's say what I continue with is not on stage, it's just on the. How would you continue that? Does not feel right to say on the stage. Yes?
On the dance floor.
On the dance floor, yeah? Okay. Anyone? Yeah? On the moon. Okay, I will continue with something similar. Let's say on the lunar what? Surface. Just pick a word. Does not need to be right. No? Soil. Okay, let's go for surface. Then I will continue. And I will add instead what would you complete the sentence with?
Step for humanity. Step for,
Yeah.
Step for human. Step for human.
Okay. So you see there are many ways to continue the sentences. But just with a few words, we are able to produce only one or maybe a couple of sentences that do make sense, even though the number of sentences that are composed of, 10 or 15 words, English words, there are a gazillion of them, right? If you combine all possible words in all possible ways. But still, you manage to do that without even thinking about it. Okay? And you see that sometimes there are ambiguities, like when we started, we don't have enough information from the context, or you are biased because you only know about Neil Armstrong and don't know about other Armstrongs. Okay? And so it means that there are different ways to complete the sentences, but as soon as you add these words, you are basically making choices. Okay? When I said I wanted to add as a next word the word perform, it really narrowed down the set of possible next words. And in this case, it was more likely that Armstrong was referring to the musician than to the cosmonaut. However, you can still manage to change this. For example, here you all proposed continuation of the sentence that corresponding to the musician, except for this one. But when you complete it like this, okay, then again you can manage to change the meaning of each word. Okay? And so ChatGPT is exactly based on this principle, except that you are not guessing the next word. It's a neural network that takes as input a part of a sentence and then manage to have a knowledge or a representation of what are the possible plausible next words. Okay? We'll see how to implement that later on, but for now, just remember that this is really just the principle which is used to build systems like ChatGPT. And so this ChatGPT model is what we call a large language model. So it's a family of different neural networks, which are basically neural networks that are built to produce sentences, okay, as compositions of tokens or words. And so if you understand this principle, then now you should understand why this large language model, they invent things because they just add tokens next words that are plausible with the current context, and they only need to be plausible. They don't need to be correct. Okay? And that's also why they cannot cite sources. So they cannot say, I know this fact because of this, article in some newspaper. Okay? Or because of this book said that. Okay? It cannot cite this source. It just produces plausible next tokens. This is also why if you ask twice the same question to a chatbot, it will almost never answer with the same answers. It's because every time the next word which is picked at random, okay? Of course, proportionally to how plausible it is, but it's picked randomly. It's also why it cannot actually count. If you ask simple questions like, what is, 10,342 times 7,360,000, you ask that to ChatGPT, and then you check the answer. It will produce something, and will say you that this is number, and will say that very confidently, but almost always it will be wrong. Okay? It works for very small computations, like 3 by 3, and so on. But if you go for bigger numbers, it fails. So it cannot count. And basically, you can extend this to the concept of compute. It cannot compute. Okay? It does not reason. It does not run some kind of program that would be used to produce the answers. Okay? You just ask, what is the next possible next one? Yes?
So I guess we're talking about an older version of ChatGPT because these two actually kind of works good now. Like last year, it was able to solve from a picture electric circuit. I don't know how to say it. It solved for me an electric circuit, so it did counting.
Yeah, but this was not a large language model. It was a reinforcement learning algorithm. So that's a whole different family of AI, which we'll see as well. But this is not based on large language models. Okay, but so the main idea is that it cannot compute or basically reason, at least until last week. There was a new version of ChatGPT released by OpenAI in which they claim, or basically they've implemented some kind of post-hoc reasoning. So instead of just producing the token one by one at random, without looking basically at the future, like the trees of all the combinations, you can basically explore the tree and then make a guess, reason on the possible answers, and then finally pick one of them. So that's something you can do, and that's something we'll see also in other contexts. And finally, it can hardly correct their own mistakes once they've been made. Okay? Once a token has been produced, you cannot rewind. You cannot take a step back. Okay? You cannot remove the token. Okay? So that's why it's very difficult for ChatGPT to correct its own mistakes. Usually, as soon as it's wrong, it will continue being wrong, and it will do that very confidently. Okay? Regardless, this is still a very impressive system. And what you should also realize is that this thing is not limited to text. You can have tokens over images, you can have tokens over sounds, and you can combine all these modalities of data into one big model. And so this is an example of GPT-4o, which is basically that system. So ChatGPT, the vanilla ChatGPT system that processes words, but also processes sounds, so you can talk to it, and it can also see and understand what you do.
Hey, I'm Alex.
And I'm Miana. Hi, Alex and Miana. Nice to meet you both. How's it going?
It's pretty good. We're trying to figure out what should we play. Do you have any suggestions?
Absolutely. How about a classic game of rock, paper, scissors? It's quick, fun, and you don't need
great. Can you count us in and sound like a sportscaster?
And welcome, ladies and gentlemen, to the ultimate showdown of the century. In this corner, we have the dynamic duo, Alex and Miana, ready to throw down in a
Okay, just count us in.
All right, here we go. In 3, 2, 1, shoot. Now, show your hands. What did you pick?
Who won?
Would you look at that? It's a tie.
Okay, let's do it again.
Round 2, here we go. Get ready. And 3, 2, 1, shoot. Let's see those hands.
Who won?
And it's another tie.
Okay, let's do it again.
All right, third time's a charm. Here we go. 3, 2, 1, shoot. Let's see those picks.
Who won?
And we have a winner. Miana's scissors cut through Alex's paper. Great game, you two.
Pretty cool. Thank you.
Thanks.
Okay, so I don't know if you realize, but if you were to tell me 2 or 3 years ago that we could do that now in 2024, I would not have believed you. We had more or less the technical components already, but to reach this level, all the research community was basically thinking that, okay, this would eventually happen. We have the tools now, and we can foresee that this will happen, but maybe in 10 years or 15 years. But here you have a system to which you can talk to, so it understands your voice. It recognizes that there are several people. It can answer back to you either in text, like in the regular interface, but also with voice. So it's able to synthesize voice. It's also able to make sense of images. So to play this game and to say who won, you have to understand first the rules of the game. Never the rules were told to the system. That's external knowledge which has been acquired somehow by training. Then it should recognize the hands. Never the system has been told what is a hand. And then that the hands can take the shape of a paper, a rock, or a scissor. And then it should recognize the two of them. It should recognize that this is my hand, this is the other player's hand, that there is this relationship between the hands, that the rock wins over the scissors and whatnot. And then conclude that one of the two players won. Okay? So that's a lot, actually. If you were trying to implement this yourself, given what you know or your basic programming knowledge, there is no way you would be able to do that. Okay, so you need something more. You need this technology to be able to do that. Okay, so this is for the introduction. I will continue with the introduction for like 1 more hour or so. And so we started with ChatGPT, but now I want to take maybe a step back and focus more on AI as a field or as a concept first. So all of you picked this course, yet how would you define AI? So what do you associate AI with? Yes? Complicated math, yeah, okay. But you could have also followed applied mathematics for that. Or you could have followed a full master in mathematics. I would say that the mathematics, we will need mathematics, but they are fairly basics. You need linear algebra, you need a bit of probability theory. That's it. Yeah?
Program tool that answers a specific problem.
Programs that can solve problems, yeah? Databases, okay. Will not see databases. Yes?
Actually, remember the definition of AI, cutting it down to 3 or 4 types. And the first one was very basically just if you have just an if in code, it's already kind of AI. It's making choice based on conditions.
Mm-hmm.
But of course, if you want to go further, then we need to add memory. That would be the second type. And then the other types, I forget how they get defined.
Okay. So to be honest, to this day, AI is still a concept that we fail to properly define. The first reason is that we cannot define intelligence in the first place. We don't have a working definition of intelligence. So we'll define AI in another way, but I just want to maybe start with a few quotes. The first one will be this one, which was said by Elon Musk in 2014, who said, so at the time, just to give you some context, in 2012, deep learning was basically really making very rapid progress, and from 2012 onward, like the field has basically exploded and was applied to many scientific and technological domains with much success. And because of this explosion, basically many people were worried that, okay, eventually deep learning is maybe the way to get there to AI, real AI, as you see in science fiction. And so that's why many, or a few, maybe more than a few, said things like, with AI, we are summoning the demon, meaning that, okay, it's very dangerous to do AI, because eventually these programs will become self-conscious, and they will decide to kill us all. To be honest, this is not an opinion that I share. I think this is complete bullshit. But yeah, you can have this opinion. At least in 2014, it was not very grounded with the breakthrough. With the state of the field. The vision we had rather in this time was this one. So this is a quote from Fei-Fei Li, the previous director of Stanford AI Lab, and she said in 2017 that basically with AI we are really closer to smart washing machines than to Terminator. And indeed, at the time, what we could do was to have computer programs, usually based on deep neural networks, that could solve very precise tasks very accurately with performance which was better than human performance. And so this is exactly this analogy. This machine can wash my clothes much better than I would do myself with my hands. And I'm very happy for that. Okay? However, the same washing machine cannot do many other things that I can do. It cannot drive my car, it cannot teach a lecture, it cannot, I don't know, walk my dog. Okay? Maybe you could build separate machines, each of them would do this precise task, but we don't, at the time at least, we didn't have any general system that would perform all the tasks that a human could perform. Okay? And this is what we call and still call narrow artificial intelligence, meaning that you have AI which is narrowed down to a specific domain or task and perform well on this task. In 2018, so this is basically an opinion which was shared by many researchers, including the main researchers in the field. So I will show you an interview by Yann Lequin. Yann Lequin is a French researcher working in the US for maybe 20, 30 years now, and is behind the technology of deep neural networks. He invented CNNs back in the 80s and the 90s, so a long time ago, and he will tell you what he thinks about AI and the state of AI. But remember, this is from 2018, so 6 years ago. In terms of AI time, this is ages ago. So the video is in French. I will then show you another one in English. Sorry for the non-French-speaking people.
Alors, je m'appelle Yann Lequin, je suis directeur scientifique de la recherche en intelligence artificielle pour Facebook. Et je travaille beaucoup sur des techniques qui permettent de faire que les machines puissent, par exemple, comprendre un texte, reconnaître une image, traduire un texte dans une autre langue, sans être directement explicitement programmés, mais en étant entraînés à partir de données. Une grande partie des systèmes de Facebook sont construits autour de l'intelligence artificielle pour que Facebook puisse décider de montrer des contenus qui sont les plus susceptibles de vous intéresser. Ce que fait l'automatisation et la robotique et tout ça, c'est diminuer la valeur des choses qui peuvent être construites automatiquement, mais augmenter la valeur des choses pour lesquelles il y a une contribution humaine très claire. Donc, ce que ça veut dire, c'est que les métiers du futur sont les métiers créatifs. Les gens ont des peurs, un petit peu, des fantasmes à cause de l'image de l'intelligence artificielle dans les films d'Hollywood, dans la science-fiction, etc. Les histoires sont toujours beaucoup plus intéressantes quand il y a des catastrophes. Donc, bien sûr, on est un petit peu conditionné par ce qu'on voit. En réalité, l'impact de l'intelligence artificielle va être incroyablement bénéfique. Par ailleurs, il y a des dangers de dérive, de mauvaise utilisation de l'IA, etc. Alors il y a bien sûr les scénarios catastrophes à la Terminator où un savant fou découvre le secret de l'intelligence artificielle et puis construit un robot qui immédiatement domine l'humanité. Ce scénario est complètement improbable. Le développement de l'intelligence artificielle ne va pas être un événement. Ça va être une progression, et ça va être une progression qui va impliquer une très large quantité de population de chercheurs, d'ingénieurs, etc. Ce ne sont pas des choses qui peuvent se faire en secret par une seule personne, ça va prendre la communauté entière. D'autre part, il n'y a pas de raison de penser qu'une machine voudra dominer l'humanité simplement parce qu'elle devient intelligente. Il y aura peut-être des machines intelligentes autonomes qui seront aussi intelligentes que les humains dans tout un tas de domaines. Il va falloir enseigner à ces robots à bien se tenir en société, mais comme on le fait avec des bébés. Alors tout ça, c'est de la science-fiction pour l'instant, parce qu'en fait, on n'a pas du tout les technologies pour ça. On n'a même pas les concepts scientifiques, en fait, pour permettre à une machine d'être intelligente au niveau de l'intelligence de l'humanité, enfin, de l'intelligence humaine. Pour l'instant, on peut faire des machines dont l'intelligence est très étroite, c'est-à-dire qu'on les entraîne pour une tâche très particulière, et pour cette tâche très particulière, elles peuvent avoir une performance surhumaine. Les machines les plus intelligentes qu'on a à l'heure actuelle sont, d'une certaine manière, moins intelligentes qu'un rat. Combien de temps ça va nous prendre à faire des progrès significatifs dans cette direction? On ne sait pas. Il se peut très bien qu'il y ait un progrès significatif l'année prochaine, ou dans 2 ans, ou dans 5 ans, ou dans 10 ans. Si ça prend plus de 10 ou 15 ans, je pense que les gens qui financent les recherches pour pouvoir faire ça vont commencer à se fatiguer et puis vouloir investir massivement dans ces domaines-là.
Okay, so this was 6 years ago. So he's mentioning. Okay, not this one. Okay, so this was 6 years ago, and he said that basically, yeah, maybe people will get tired if there is no breakthrough happening in the short term or in the mid-term, and this is actually what happened. Okay, 4 years later, if we fast forward, ChatGPT happened. What he says also is that this will not be an event, but this will be an incremental progress, and this is also true. The technology behind ChatGPT and other chatbots was actually contributed back in the 2017. Okay, so there was a lot of improvements, trial and error, but still, really, in 2022, everyone could notice or realize, including the larger public, what we can do today with AI. Okay, and from there on, there was a switch in opinion also from within the scientific community about the dangers about AI. It's still split. You have a whole continuum of opinions with Yann Lequin on one hand saying that everything will be fine, to the other extreme saying that we should stop working on AI, it will eventually kill us all. Okay? On this side, you have Geoffrey Hinton, which is much more cautious than Yann Lequin. So Geoffrey Hinton is also an important figure in AI. He's one of the, I would say, godfather of the field. He basically invented a way to train neural networks, which is still used today. He invented that back in the 70s, in the 80s. He worked at Google for many years. He's now retired. He actually retired and removed himself from Google because he was seeing the danger and wanted to have he wanted to basically be able to say freely what he was thinking about the field. So let me show you that.
The man widely seen as the godfather of artificial intelligence has quit his job at Google, warning of the dangers of AI. Dr. Geoffrey Hinton's pioneering research on deep learning and neural networks has paved the way for current AI systems like ChatGPT. But in a lengthy interview with the New York Times, Dr. Hinton said he now regretted his work and is worried that AI technology will flood the internet with misinformation. Google responded in a statement saying, "We remain committed to a responsible approach to AI." Dr. Hinton has been telling the BBC how these systems can know so much.
The kind of intelligence we're developing is very different from the intelligence we have. We're biological systems, and these are digital systems. And the big difference is that with digital systems, you have many copies of the same set of weights, the same model of the world. And all these copies can learn separately, but share their knowledge instantly. So it's as if you had 10,000 people, and whenever one person learned something, everybody automatically knew it. And that's how these chatbots can know so much more than any one person.
Well, Dr. Hinton also told the BBC the rate of progress is worrying.
Right now, what we're seeing is things like GPT-4 eclipses a person in the amount of general knowledge it has, and eclipses them by a long way. In terms of reasoning, it's not as good, but it does already do simple reasoning. And given the rate of progress, we expect things to get better quite fast. So we need to worry about that. Right now, they're not more intelligent than us, as far as I can tell. But I think they soon may be.
Earlier I spoke to Junaid Mubin, author of Mathematical Intelligence. I asked what he makes of the AI warning.
I think this one is to be taken seriously because of where it's coming from.
Okay. So this was in 2023. The same year, a few months later, Yann Lequin, the same guy as in the previous video, where in the first he basically says that, okay, you have nothing to worry about, they are not smarter than a rat, and even if they would eventually become as smart as human, there is no reason to believe that they would kill us all. Okay, there is because they don't have any sense of purpose, and there is no. It's not grounded to say that. Basically, in 2023, even though ChatGPT happened, he still has the same opinion. Okay, so we just show you that very quickly. It's short.
We do not have a blueprint for a system that would have human-level intelligence. It does not exist, the research doesn't exist, the science needs to be done. This is why it's going to take a long time. And so, if we're speaking today about how to protect against intelligent systems, taking over the world, or the dangers of it, regardless of what they are, it's as if we were talking in 1925 about the dangers of crossing the Atlantic at near the speed of sound when the turbojet was not invented. We don't know how to make those systems safe because we have not invented them yet. Now, once we have a blueprint for a system that can be intelligent, we'll have a blueprint probably for a system that can be controlled as well. Because I don't believe we can build intelligent systems that don't have controlling mechanisms inside of them. We do as humans. Evolution, can build us with certain drives. We can build machines with the same drives. So that's the first fallacy. The second fallacy is it is not because an entity is intelligent that it wants to dominate or that it is necessarily dangerous. It can solve problems. You can tell it, you can set the goals for it, and it will fulfill those goals. And the idea that somehow the system is going to come up with its own goals and take over humanity is just preposterous. It's ridiculous. But to that point, and to the point that Stuart and Conor just mentioned, you can imagine an infinite number of scenarios when all of those things will go bad. You can do this with any technology. You can do this with AI, obviously. Sci-fi is full of it. You can do this with turbojets. Turbojets can blow up. There is lots and lots of ways to build those systems in ways that will be dangerous, wrong, they'll kill people, etc. But as long as there is at least one way to do it right, that's all we need. And so, for example, there's technology that was developed in the past that was developed at the prototype level and then was decided that it should not be deployed because it would be too dangerous or uncontrollable. Nuclear-powered cars. People were talking about this in the 50s. There were prototypes. It was never deployed. Nuclear-powered spaceships, same thing. So there are mechanisms in society to stop the deployment of technology if it's really dangerous and to not deploy it.
Okay, so now you have the two extremes in the continuum of opinions about AI. You pick wherever you want to be along that spectrum. If you want my opinion, I'm closer to Yann LeCun than to Geoffrey Hinton. I think everything will be fine, but I might be wrong. Who knows? We'll see. Yes?
What's your opinion? I didn't get you.
That I'm closer to the opinions of Yann LeCun. I don't think anything bad will happen, at least not tomorrow. And I think if eventually we can build these systems to be really truly intelligent, we'll also be able to control them, at least in some way. Yeah. All right. Yes?
Do you believe we will achieve, in decades maybe, general AI?
Yes. Yeah.
That's broad statements.
I mean, given the rate of progress, I'm in the field since 2010. I would not have said that in 2010, but given how fast it has evolved within my short career, yes, I would believe that in a few decades we will laugh at the level we were back in 2024. Yes.
I'm surprised by this answer. The question took the answer stomach. So it did not define general AI. Is it for you the kind of AI that would be able to do things on different fields, like a wide range of different skills? That's what you...
Yeah, I mean, we can talk for hours about definitions. I will mention a few of them. But yeah, you can have systems that already are fluent in many scientific fields. ChatGPT is one of them, in a sense. Okay, you can argue that, okay, maybe it's not as good in everywhere, but I'm not either. And I would consider myself as a generally intelligent being, and you too, no? Okay, so what about a definition of AI? So this is something I will discuss a bit, but then we'll go beyond that. So in the 60s, Marvin Minsky, who worked on neural networks back then, said that artificial intelligence is the science of making machines that do things that would require intelligence if done by men. Okay? So that's a very broad definition which not really say what is AI. It just say that, okay, if that something can do that, then it's intelligent. But according to this definition, many things could be labeled as AI. If you just take a regular computer program, it's a machine that do things that would require intelligence if done by man. Okay, if a simple Python program doing the multiplication of two big numbers is something that would require some of my intelligence if I were to do that myself. Therefore, it's AI. Okay. You may agree or disagree, but you see certainly the limits of trying to define AI in the first place. In the 50s, Alan Turing proposed a test, which we call the Turing test, or the imitation game. And he said that, okay, maybe to test if a machine is intelligent, we should basically evaluate that machine. And we would say that a computer or program or some entity or machine passes the Turing test if a human operator, after posing some written questions, cannot tell whether the written response, the written answers, come from an actual human being or from a computer. And if you cannot tell, then you say that the machine passes the test, therefore it's intelligent. Again, I don't think, I mean, now today in 2024, we have systems for which it would be very difficult to say if the text produced is human produced or not. But would you say that, I don't know, ChatGPT or something even simpler than that is generally intelligent? I don't know. Also, one of the limits of this test is that an agent would not pass the test without the following requirement. I mean, it's not it's rather all the facets that you would evaluate to make sure that you pass the test. So it comes with requirement. For the machine to pass the test, it should be able to process natural language, either in text or in voice. It should be able to have some kind of knowledge which is represented somehow. And it should have accumulated some knowledge. It should be able to reason in some way. It should be able to learn so it should be able to learn new facts or new rules or new things, and then to use this new knowledge to produce new answers. Then you have other versions of the text, of the test, like the total Turing test, in which you also have you put the program inside a full robot, and in this case, it should also be able to see and understand what it sees and to move in a body, okay, in a robotic body. So this test was proposed in the 50s, so 70 years ago, but it's still relevant today because it's still very difficult to have a system which fulfills all of these requirements. Even ChatGPT would not fill all of them. The main one being the reasoning part. It's very difficult to implement the reasoning in these systems. However, this test comes with limitations. If you are the actual operator, the actual human being trying to assess whether or not the text that you see, let's say, is human-made or not, basically you would certainly focus on small mistakes, like you would try to spot human-like errors, or you would try to maybe use some kind of linguistic trick to basically try to trick the system into saying wrong things. But you would not really be trying to probe for the actual intelligence of the system. You were just trying to basically fail the system. Okay? So it tends to focus on this. However, I believe that it seems more important to try to study the principles underlying intelligence rather than to try to replicate one of them. Okay? Because at the end, maybe you would have a system which passed the test, but the reason it might pass the test is because it managed to avoid all these tricks or managed to reproduce errors that are human-like and so on and so forth. Okay? And so an analogy would be this one. So you don't define aeronautics as the fields of making machines that fly so exactly like pigeons that they can fool even other pigeons. Okay? it seems so ridiculous when you say it like this, but it's true also for AI. Why should we define AI in this way? In trying to define machines, or we would not define the field of AI as the field of making machines that reason so exactly like humans that they can also fool other humans. Okay, but the Turing test is basically probing for that. A modern definition of AI is given by the very recent European AI Act in its third article, and it says that an AI system is a machine-based system that is designed to operate with varying levels of autonomy, and that system may exhibit adaptiveness after deployment, so meaning maybe you program it to do something and then it can change, it can adapt on its own without being reprogrammed, and that for explicit or implicit objectives infers, so reasons, from the input it receives how to generate outputs such as predictions, content recommendations, or even decisions that can eventually influence physical or virtual environments. So again, in my opinion, this is a good definition, but maybe certainly too broad. It's good because you could define modern AI system with this definition. However, also regular programs would fit with this definition. Like if you think about a thermostat, something very boring that you find in your house with a very short computer program inside, it's a machine-based system. It's designed to operate with varying levels of autonomy. Of course, you don't want to reprogram the thermostat every day. You want it to run and to be autonomous. That may exhibit adaptiveness after deployment. Of course, it will adapt depending on the current temperature. And that, for explicit or implicit objectives, infers from the input it receives, for example, from sensors that you would have in your house, measuring the temperature, how to generate outputs, such as prediction, content, recommendation, or decisions. In this case, it will produce decisions, commands to be sent to your boiler that can influence physical environment. Of course, you want it to heat the house. Would you say that a thermostat is an AI? So the European Union would say yes. But again, I think the main reason is that they want to be on the safe side, so they will be certainly broader than what they should have been. And certainly, modern system will still fall inside this definition, but in my opinion, it's too broad because it also includes too many things that are not really AI. Okay, so as you have seen already in what I've presented, AI is not something new. So the field itself was born more or less in the 40s, 50s, in the early days of AI. At the time, people were very excited because also at the time, there was a lot of progress together with the inventions of computers and the progress we did in terms of computing. And already back in the 50s, you could find programs that could play checkers, that could reason and solve mathematical theorems. At the end of the 50s, the very first neural network was invented. So the perceptron was invented by Rosenblatt back in the 50s, and so on and so forth. The term itself, AI, was invented in 56 at the Dartmouth meeting. And so this meeting was involving these folks, very smart, including, for example, Shannon there and other important people. And they were so full of themselves that they described this workshop as just a summer task in which they would say, OK, we'll proceed. And the goal of the workshop is the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. And they wanted to solve this problem within 3 months. 70 years later, we still don't have the answer. OK, you can watch this video. This is from the 60s, in which already in the news we were talking about AI and what it could do. In this case, you could already use AI to recognize images and also to translate a bit of text. And in this case, a lot of progress, or investment was made during the Cold War, basically to have some kind of automated translation system to go from Russian to English and to try to understand what they were telling about the American. Okay, fast forward 70s to 90s, because of a book by Minsky, the same guy, this one. So in '69, he wrote a book in which he said that basically neural networks, they cannot represent all functions. And this was misinterpreted. He did not exactly say that, but people basically summarized what he said as that. Neural networks, basically, they are a dead end because of these mathematical results. And because of that, basically all the research on neural networks stopped, except maybe for a few researchers back in the 70s. And so researchers worked on other systems like knowledge-based systems that are based on logic. Expert systems were something that the industry was very excited about. But again, it was very, the hype was maybe too great. And at the beginning of the 90s, it basically burst. And again, then people started disregarding AI again. In the beginning of the 90s up to now, the neural networks returned, so people started working on them again, even though from 1995 up to, I would say, even 2010, really the research community in AI was not focusing at all on neural networks. Because at the time, people, except maybe for Yann Lequin and a few others, could not make them work. But what happened is that because of the availability of large data sets, like with the creation of the web, data become something that everyone can access in large volumes. Also with the development of new hardware, very fast computing resources like GPUs, all these things together, also with improvements in terms of the algorithms, the models, and so on and whatnot, eventually neural network made a comeback, and in 2012, they won a very prestigious competition, and they won by a very large margin. It was a competition about recognizing images. At the time, all the other approaches were based on other classical machine learning models, like linear models, supervector machines, and so on and so forth. But here in 2012, the improvement was larger than 10% in 1 year. Usually, the improvement was very incremental, like 1%, maybe 0.5%. Here in one go, 10% more accurate. And from there on, basically, the community switched completely. Okay, they recognize that, okay, these things, they do work now. And so everyone switched. Now all the computer vision is based on neural networks. You will have a very difficult time to find a research paper in computer vision not using a neural network in one way or another. And this is true for almost all fields of computer science, but also all fields of technology. And I would say, I would go even beyond that. Many scientific fields are also switching, or have actually switched for a long time now, to AI approaches like deep neural networks. Okay. All right. Do you have questions so far? Okay, so now it's a good time to take a break. Let's say we resume at 9:40. Okay. could resume. Okay. All right. So in the first part of the introduction, we talked about AI as a general concept. I gave you a few opinions about what it is, its possible dangers, its applications. In the second part of the introduction this morning, I want to focus on something specific, which is deep learning. So deep learning is basically the technology which is really behind everything, all the advances that we've seen about AI in the news or that you've maybe used yourself. I'm quite certain that all of them are based on deep neural networks. So deep learning has really become something fundamental in AI. It's almost synonymous now with AI, not completely. And I want also in this course to show you that, yes, AI is not only deep learning, but deep learning has become a major part of it. So that's why I want to focus on that this morning. We'll have lectures afterwards on the topic also. Okay, so let's start with something simple. Let's start with data. Okay? So as you will do certainly, maybe some of you in the future, you will have to implement or to train some AI system, some neural network, to do something. And the very first ingredient that you need is data. Okay? And so the very first thing that I say to almost all students, before diving into the certainly exciting details of deep neural networks, training and whatnot, the very first thing you should do, before all else, is to look at the data that you have. Okay? Just by looking yourself as an intelligent human being, you can do a lot. Okay? So let's say this is the data that you are given. Let's say they correspond to medical records about patients, and you summarize this data as pairs of numerical values. Each dot corresponds to a patient, and for each patient, you know the age and the blood pressure. Okay? And your goal is to implement a very small program that would be able, given the age, to give an estimate of the blood pressure of that patient. How would you do that? Given what you see when you look at the data. Yeah. A regression? What kind? Okay? So meaning you want to fit a line like this, or maybe like this, I don't know, to the points. Okay. Anyone else? So for all the other ones. Okay, so let's say we have X and Y, age, pressure, okay, and we have a small data set, okay, like this one. Okay, what you want is to write some function, a computer program, that would take X as input and would produce a good guess of Y. Okay? So you want to find a relationship like this. Okay? And one possible relationship that you could assume is a linear relationship in which you say, okay, I will grossly summarize the X to Y relationship as a straight line. Okay? Meaning that you will make the assumption that F, sorry, okay, so this is a choice that you make, it's a model that you make. You say that Y is a line. Okay? which is parameterized by some coefficients that you associate with x and some offset. Okay? So if we are in this 2D case, of course, this is not a vector, it's just a scalar. And this is also just a scalar. So you have ax plus b equal 1. Okay? And you have two parameters. Okay? These things, a and b, are what we call parameters. Okay? And they are scalar values, numbers, you would have to figure out. Okay? Because depending on the values that you set for a and b, you could have this line, or you could have this line, or you could have this line. Okay? Each of these lines is mapped to one of these parameterizations in terms of the parameters a and b. Okay? If you increase b, you will basically push up the line. If you decrease it, it will lower. Okay? And if you play with a, it will rotate the line. Okay? Now, how do you find good values for a and b? Yeah. You minimize the error function. Okay, how would you explain that to all the other ones? What's an error function? Okay, so that's a very good point. So what we have is access to the training set, to a data set of points which we call a training set, and which you can use to basically identify good values for the parameters. And one principled way to identify these good values is to say, okay, I will identify values for A and B such that the prediction error that I make on the training set is as small as possible. Okay? Meaning, given x, for example, this one, x1, you know y1. Okay? So given values of a and b, you can compute a prediction a x1 plus b, and that produces an estimate with a hat for the blood pressure. Okay? And what you can do is to compare if this prediction is close enough to the actual value that you have in your training set. Okay? So that's the idea. Okay, so just to go over the slides, the machine learning approach to this problem is to assume a model. Could be as simple as a line. Later on, we will extend that to full and very complicated neural networks, but the recipe will remain the same. We want to write a computer program that takes as input the age and produce a prediction or an estimate of the blood pressure. In the machine learning approach, you would assume a model like a line in which you have many knobs, parameters to tune. Okay? And so if you, in this case, you have two knobs, the offset and the slope of the line. Okay? If you play with them, you will either push up or turn or rotate the line. Okay? And eventually, according to some objective function that you will define, like minimizing the error between your estimates and the actual values in the training set, you would identify some values for the parameters, which you would use then to make predictions. Okay? So that's a very simple recipe. We'll implement that later on during the course. What you should understand is that this very simple recipe of assuming a model, a parametric model with many knobs, and using a training set to adjust the knobs, is basically what we do when we do deep learning. Except that we don't fit a line with two parameters. We fit a gigantic neural network, which is nothing else than a very complicated, not so complicated, but somehow complicated mathematical functions, which comes with parameters. We don't have two parameters usually. In the standard regimes of today, we have neural networks with at least in the tens or in the hundreds of millions of parameters. To implement a system like a transformer, which is used to power ChatGPT, the model comes in the hundreds of billions of parameters. Okay? The data that we use, so basically deep learning scales up this recipe by considering much more complicated and bigger models with more parameters, first. Second, you train this neural network not on very small set of data, but on very large data sets. And when I say large, it's really large. So can you make a guess about what is the training set used to train the neural network behind ChatGPT? Yes. First step one, download the internet. Then train. So this seems crazy, but we are really close to this regime. And it's also why only a few companies, private companies with immense resources are able to do that. Like, we could not, even all of us together, download the internet. They can. Okay? And in terms of number of tokens or words that represents, we are in the region of trillions, thousands of billions of tokens. So of course there is no way any human being would be able to read that during its lifetime. A neural network, a transformer can do that several times during its range. Third, so bigger model, bigger data set. And the third is the hardware, the computing resources that you need. They are really enormous when it comes to deep learning. You need dedicated hardware to train these neural networks. You can do you can train some models on a laptop or maybe on a dedicated machine, and that will work to some extent, and you will be able to have good results. But if you want to reach the scale necessary to build an actual large language model, let's say, you would need a full data center with hundreds of thousands of machines, each of them with full of GPUs. So for example, I don't know, so I suppose you all know Meta, the company behind Facebook. They recently made an order to NVIDIA. NVIDIA is the manufacturer of GPUs, and they wanted to buy at once. Can you guess how many GPUs? 4 millions? 40 millions? That's a bit much. $600,000 of them. You can fill in several data centers just with that. Just to have, trying to picture how big that is a phenomenon. Okay, so what do we do with these neural networks? So what we've been doing so far in the deep learning community was to train specialized neural networks. And what we've discovered is that these neural networks, they are able to reach usually superhuman performance on many complex tasks that for a long time were thought to be really out of reach for machines. Like you can train a neural network, and that's very standard now, to process an image and to understand the content of the image, meaning it can identify all, for example, the cars or all the objects or all the people up to the pixel precision in the image. So you can, this is what we call image segmentation or object detection. You can also do in vision pose estimation. So given, for example, that you've recognized that there is someone, you want to estimate the pose. Like this part is the head, this part is the body, these other parts are the legs, and so on and so forth. This is something, for example, that implicitly this ChatGPT system would need to be would have to do if it wants to recognize the hands and the shape of the hands forming a paper or rock or scissor. In vision, you can also have neural networks that take a 2D image and try to estimate a third dimension, like the depth associated to each pixel. So for example, if you are in your car and I show you this and I point to this part in blue, you can all tell me very easily that this part in blue is very far away from you. But how do you teach that to a neural network? And that this part, the road is much closer. But because of the perspective, these pixels in the same color, they are much further away in the image. So that's something that you can also estimate with neural network. That's a problem which we call depth estimation. There are various other computer vision problems that you can solve with neural networks. Something maybe a bit more different is the fact that you can also have neural networks that are able to play games and very complicated games for humans, like the game of Go, for very long because of the complexity of the game. Like the number of next moves that you can do in the game of Go is in the hundreds. So the tree of combinations is like gigantic. Because of this reason, for very long, this game was thought to be unreachable for machines. Already some years ago, I think it was in 2015 or 16, the best human players were beaten by a computer using deep neural networks and other things, but mainly neural networks. Since a long time, you can also have systems that manage to combine several modalities of data, like images and text. So for a very long time, people have been developing, for example, a system that would take an image and would produce a sentence that describes this image. So you have a few examples. Or for also a very long time, researchers have been trying to make systems understand text to build, for example, question answering system. You feed a piece of text and then you ask questions. And you see if it manages to answer these questions. Again, this seems very simple. We can do that very early. You can ask simple questions like this to a 6 or 7 or 8 years old. It will do perfectly usually. But to do that with a machine, that's much more complicated because depending on the question, you may have to reason, to associate facts from the text before, and so on and so forth. Okay? So these are the things we've been working on since 2012 in the deep learning research. Okay, but you might tell me, why do we care about identifying cars in images? Why do we have thousands of researchers working on this problem? Is that really that important? Don't we have better things to do? So for us, these tasks, they are actually just a pretext. Because if we can solve this task, we can actually use the same tools to solve much more interesting problems. You should view that as primitives of some sort that you can transfer to other domains. And so these are applications, for example, in the medical domain, in which, for example, this is the image of a histological slide, so an image that you would acquire with a microscope of a tissue, and you would like to identify that, okay, this part corresponds to a cell of this kind, this part is a tissue which maybe should not be there, maybe it's malignant, and so on and so forth. But actually, the technology you would need to do that is exactly the same as this one. Okay, if you can train a neural network to identify car in images, of course you can train the same neural network to identify cells in tissues. The neural network does not even know what it's looking at anyway. You can also, so you have other applications. This one is in the case of fMRI data, where you acquire images that are very noisy and you would like to remove the noise. That's something that you can also do with deep neural networks. You can also detect, for example, how do you call that? Grain de beauté in English. Mole, maybe. I know there is a specific word, but okay. Anyway, you understand. You can use a neural network to spot them and to classify them. Is it something that I should not care about? Should I go to a doctor if I see that? And again, we can do that with the neural network. If some of you have a smartwatch, like an Apple smartwatch, maybe you have guessed, or sometimes you wonder, how does it know my current, if I'm healthy or not, or if I should get up or not? Or maybe it will warn me the next minute that, okay, maybe you should go see a doctor because there is something really wrong with your body. Actually, from the light sensor at the back of the watch, you can estimate the full cardiovascular system of someone, and from that, infer the health of someone and maybe make recommendations. And again, you do that with neural networks, the same kind of neural network that you would use there. Okay, so this has been going on for a long time now. However, something important happened in 2017, which is this paper called Attention is All You Need, which is a paper written by researchers at Google and at the University of Toronto, in which they propose an architecture, a very famous architecture now, which is called the transformer architecture, which is this thing. Okay, don't worry, you don't have to understand how it works yet. When you will follow deep learning, I will ask you all about all the details, but for now, you can just say, okay, it's a neural network of some kind. And what is a bit marvelous about this architecture is that it's the very first architecture with which we manage to see improvement by just feeding more data. Usually with the previous specialized neural network, like this one or this one, usually they were saturating very quickly. Okay, you may have a big data set and it learns well, but if you put a 10 times larger data set, it's not necessarily 10 times better. With the transformer, the story is a bit different. What we see, and that's a bit maybe disappointing for us as researchers, but this is what you observe empirically, the more data you feed to this transformer architecture, the better the model, the better the results. The more parameters, so the larger the model, the deeper the model, the better the results. And the more compute, so the longer you train, the better the model. So just go for a brute force approach and you will get state-of-the-art results. And actually, this architecture is so important now that even though before we had specialized neural network to solve one or the other task, these days, almost everyone is using exclusively transformers to solve anything. Yes?
So is this concept not having problems with overfitting issues?
We can talk about that offline. Actually, and that's also a mystery in deep learning, even though we have models with billions, hundreds of billions of parameters, we do not overfit. Okay, so if you scale this recipe to this regime, then you get modern applications of AI. So we have talked already about ChatGPT. There are alternatives to these chatbots. I don't know if you know about Claude. Claude is a chatbot from Anthropic AI, another American company. Just to give you a taste about what it can do. Okay, so there are other alternatives even. So you have ChatGPT, Claude from Anthropic, you have Le Chat from Mistral, it's a French company. Yes?
So compared to ChatGPT, Claude is more known for, as you said, like the big pieces of ChatGPT was calculations and ever Claude is.
I mean, they all claim to be able to reason now in some way or another. Depends which benchmark you look at. It's evolving very fast. What I tell you now in December will be wrong because someone else will have made a better model. Just saying all these companies are building this. They are all evolving very fast. You have also open source large language models, which are also evolving very fast. What is maybe really new with these applications is, I would say, and that's a very big change, is the interface. Like, before ChatGPT or these other systems, if you wanted to do AI, okay, to build one of these specialized neural networks, well, you needed to be a good programmer, you needed to have a good understanding of deep learning libraries, you needed to know the whole recipe to build and train and validate the neural network. So basically, you needed at least a master's degree to be able to do that, to use AI. What is new since ChatGPT is that even your mom can use AI. You just talk to it. And certainly, maybe it will talk to it in a better way than us engineers or computer scientists, which thinks in some other way. Okay, so really the change of, I think one of the most important changes in the last 2 years is the interface, the way you use this system. Of course, to build them, and that's what we want to do as engineers or programmers or whatnot, that's also interesting, but just to use them, now there is no barrier anymore. Just open a web page, you talk to it, and then you get these answers. Or you open your smartphone, you have also applications that come with all of these chatbots. Just talk to it in text or with your own voice, and they will answer. So I think that these assistants will really enable many applications that are yet to be developed. So the chatbots interfaces like this have been what we have been seeing so far. Another example, which I think is very good, is coding assistant. So when you open your code editor, like, I don't know, VS Code, you can actually now interface these editors with AI systems to help you code, help you program, debug your own code, or even code for you. So that would seem crazy. How can you do that? That seems very complicated. I need to study for 5 years to be a programmer. That seems impossible. So this is a video of an 8-year-old girl building in less than 1 hour a web server in which you have an interface through which you can talk to Harry Potter. Can you do that now in less than 1 hour with the knowledge that you have? It's also running in the cloud. So let's see. I will not, the video is a bit long, but let's look at the first minutes.
Hello, everyone. And today, I'm going to show you how to code with cursor. Then you get a terminal. I'm going to say new terminal and terminal.
Okay, but so you get the idea. It becomes very easy to do things we were thinking were quite difficult. Just look at the video. And so I think these applications will really change in the next few years what we can do and how we use computers. And I'm not, when I show you that, don't despair and think you should do something else than studying computer science. We still need people to actually build this system. And actually, she does not understand anything she is writing, which maybe tells more about web applications and web development, but that's another story. Anyway, okay, but it shows that maybe you don't need to understand that to build these applications either. Okay, another application maybe a bit different. So when you talk about AI now, it's often synonymous with ChatGPT and these other things, but there are plenty of other and maybe more interesting applications. One of them, which is often associated with the AI, is the case of self-driving cars. So who thinks self-driving car is something maybe we'll have in 10 years? Who thinks that will happen maybe next year or in 2 or 3 years? Who thinks this is already the present? Okay, if you go in California, you will see self-driving cars on the road. They are there. If you go in some places in Asia, also you will find them. Why we don't have them in Europe, that's another story, but it's not the future. And that's, in my opinion, a very beautiful application of AI because it involves many of the concepts we'll see during this course, which is the fact that to build a system like a self-driving agent, the agent needs to basically understand its own environment, the other cars around it, the pedestrians, the obstacles, and so on and whatnot. And then it needs to infer what will happen in the future in order then to make decisions like moving forward, turning right, turning left, and so on and so forth. And so this is a video from 2 years ago from Waymo, the company building self-driving cars. And it explains all of that.
So much emerging technology is just a show. So one can be forgiven for not being able to distinguish fact from fiction. Take this car, for example. Can it drive autonomously or not?
The short answer is absolutely.
That was Shweta Shrivastava, Senior Product Lead for Driving Behavior at Waymo.
What you're looking at is the Waymo driver in action. Adapted for a variety of vehicle platforms, it is the most advanced, fully autonomous driving technology in the world today.
What you notice pretty quickly is that these aren't normal vehicles. Take this Jaguar I-Pace, for example. It's been equipped with an elegant array of sensors and software, which allows it to move through the city on its own.
That's correct. The Waymo driver is a combination of custom-designed hardware and software that is responsible for performing the entire act of driving.
That was James Philbin. He's an engineering lead on the perception team at Waymo. I asked him to break down the technology for us a bit more.
The Waymo driver handles the task of driving in 3 basic steps: sense, solve, and go. It's the way we describe the highly complex process of acquiring information, processing it, and moving through the world safely.
So, what goes into all that sensing?
The sensors that the Waymo driver uses are incredibly powerful, using a combination of LiDAR, cameras, and radar. It can see up to 3 football fields in any direction and can detect sirens from emergency vehicles, which allows the Waymo driver to visualize the world around it in milliseconds to a high degree of accuracy.
Okay, sense makes sense. But what do you do with all that data?
Good question. The system calculates the predicted future behavior of each relevant agent in the scene. Then, with a strong foundation derived from artificial intelligence and machine learning algorithms, the Waymo driver crunches all that data and calculates a safe route.
So just a comment there. So you saw these maps of people in yellow and the blue background. This is actually one of these tasks of estimating, for example, the depth associated to each pixel, which is one of these tasks of one of these specialized neural networks. So you should see that from an engineering perspective, we are just composing things we knew how to do already from a few years ago together into a full system. And why is this interesting? Because if you can estimate the depth associated to pixels, you can reconstruct the 3D geometry of the scene, and so you can identify where the car is currently on the road, where are the other cars, how far they are, how fast they are moving, and so on and so forth.
But responding in real time to the evolving traffic environment.
If I understand correctly, this means the Waymo driver continues to learn as it goes, is trained and tested on scenarios that it's never seen before, and can differentiate safe and comfortable driving behaviors from hazardous and uncomfortable ones.
Yes, well done.
Why, thank you. The final step in the sense, solve, go methodology is perhaps the most straightforward. Go.
Once the Waymo driver has determined the path to take, our advanced motion control systems allow for smooth acceleration and braking on hilly streets or managing bumper to bumper traffic with safe and natural driving movements.
So it's really here, right now in cities. Not smoke and mirrors, but true autonomous driving technology. Waymo is taking what was once futuristic sci-fi and making it non-fiction. And like all great technology, all that number crunching, all that data just fades into the background. And you realize the dream of riding in a fully autonomous vehicle to your favorite dinner spot isn't just a vision of the future. It's actually happening right now.
Okay. Okay, next, I will not show you all the videos, but feel free to watch them later on. But just again to motivate what you can do with AI. So many also applications of AI these days. So you can use them for conversational agents to build self-driving cars. There are also maybe more impactful applications like for the energy transition. There are also many applications of AI. And you can watch this video from NVIDIA, which is showcasing a few of them. In the medical domain, there are also plenty of applications. So this is from 2018. So since then, we've moved on a lot. But if you are interested also by medical applications, you will also see many applications there. One of them being this analysis of microscope images. Something that actually, if you go in regular hospitals, it's often done manually. You have someone looking at these images, which is paid very expensively, and then that's it. You could automate all this work. Okay. What I think, however, is much more interesting than automating things that human can do, because maybe you may have reasons not to do that and good reasons not to do that, and I would agree with you. What I think are the best AI applications, or deep learning applications, are the applications to problems that no human can solve. And there are actually more and more examples of this kind. There are things that we could not do before, that no human could do before, that we can now do thanks to AI. Okay? One of them is, so I will just pick a few of them, but one of them is the AlphaFold system. So do you know about AlphaFold? Have you heard about this? So AlphaFold is a neural network which takes as input, so this is in the biological domain, it takes as input a sequence of amino acids, which is basically the constituents of proteins, like it described as a long chain. And a major problem for biologists, microbiologists, is to recover the 3D structure associated to this chain. Because from the 3D structure of a protein, you can basically understand its function, and from the function of the protein, you can basically understand the macroscopic composition of these proteins. Like you can start understanding the behavior of cells, but from its own little bricks. You can also try to or manage to discover new drugs, and so on and so forth. So this is a very major problem, and until not so long ago, the way you would try to estimate the 3D structure of a protein was by doing long and costly lab experiments. So you hire someone, like typically a PhD student, because they're cheap, to work for months in a lab using some very advanced chemical analysis, and they are able, after a few months of work, to recover the 3D structure of one protein. How many proteins do you think exist? More than that.
More than there is atoms in the universe.
Yes. Yeah. And we estimate that the number of proteins or molecules that have some kind of pharmacological effect. So it's really just a small set, or smaller set among all the sets of proteins. It's in the order of 10 to the 60. 1 and then 60 zeros. So there is no way we'll be able to hire 10 to the 60 PhD students. Okay? So what do we do? So this is really a problem that we can't solve with traditional techniques. What we have managed to do, or what Google DeepMind managed to do with AlphaFold, is to train a neural network which is able to take us into the sequence of amino acids, and then be able to guess and very accurately the 3D structure associated to this protein. And it's so accurate, it's not perfect, but it's so accurate that actually biologists are now using it and bypassing months of very tedious work. Certainly, this work eventually will get the Nobel Prize. It just takes some time, but you should not be surprised if in a few years from now, Google DeepMind wins the Nobel Prize of Medicine, for example, because of this work. Okay, so you have a whole video about that, and more broadly, you will see many applications of AI in science, which I think are really interesting and exciting. Another related problem is the problem of discovering new drugs. So again, how do you think we identify new drugs to cure disease that we can't cure yet? Yeah?
We look for the ones that already work and we try to find analogs.
Yes, so you can do that. So we have a catalog of working drugs, and maybe we make a good guess somehow and manage to reuse a drug that previously was used, I don't know, to treat some disease to another, and maybe that works. Usually that's how it's done, by trial and error and good guess, a lot of chance. How would you do that, or how could you do that in a way which is more systematic and automated? Because again, the space of possible drugs is just so large. So one way, again, is using deep learning. You can have neural network that takes as input a molecule described in some way, and then directly infer or estimate some of its properties. And then you can use that as some kind of super powerful filter to quickly go over thousands, millions, billions of molecules, estimate their properties, and then only keep the ones that do look promising. And then in this smaller set, then you continue, you actually do the wet experiments and so on and so on. And actually, this paper from, when was it? I don't remember, but from some years ago. So it was one of the first instances and working instance of this strategy in which they've used a deep neural network to discover a new kind of antibiotics, which is like super important. Another one, and that will be the last one today, is the case of weather forecast. So do you know how we predict the weather for tomorrow or the next week? Yeah, what about it? Yeah, so you can, okay, so you can observe from previous measurements and things that happen that okay, low pressure and high pressure have an effect. It seems to be the cause of, for example, rains. But how can you push this to actually make weather forecasts and tell them, okay, tomorrow morning in Liège it will rain, then in the afternoon it will be sunny, the temperature will be 60 degrees, and then the next day it will be, no. Yeah.
Tries the entire space around the Earth, and then we take measurements pretty much everywhere, and we try to guess where the heat flux is going to go, where the wind is going to go, and that our prediction.
Okay, that's a good strategy. But first, okay, you say you take measurements a bit everywhere. Is that realistic? Can you put weather stations everywhere on Earth? So you have a huge problem, but this is something we have to deal with. You have a data problem in this case. You can't measure everything. You have a few weather stations, you have a few satellites, and then you have to make your best to make a good guess of the state of the system, of the Earth system. Okay? And then you say, from this, we guess what will happen. How do we make this guess? Yeah.
Can say that maybe it is based on the patterns from the past experience.
Sure. Yeah. And how have we summarized these patterns? What do you think?
Physics models.
Yes? Like which one?
Well, there's one for physical airflow, another one for pressure.
So that's what like atmospheric science is all about, how to model the atmosphere. And usually it's some extension or alternative to simply the Navier-Stokes equation that you can start at the current guess of the system, that you unroll forward into the future, and then you unroll up to 2 weeks into the future, and then you use that as your forecast. That's how it's done. That's how it was done. These days, we are using more and more deep learning neural networks because these neural networks, they make predictions that are more accurate than Navier-Stokes. Because these equations are incomplete. Okay, there are plenty of things that do happen that are not taken into account into these equations. And so GraphCast is one of the systems. It's a big neural network that makes predictions for the whole Earth for the weather in the next days. And it's based on what we call a graph neural network, which takes into account the spherical topology and so on and so forth. But what is important is that, okay, we can make more accurate predictions with this, but also it's much faster. If you count the computing resources that you need to make regular weather forecasts with scientific simulations of Navier-Stokes equations, well, you need a whole data center to do that. Here, you just need a big machine, but just one of them to run this neural network, and in less than 2 minutes, you will have the forecast for the next 2 weeks. Okay, so these are, in my opinion, more exciting and important examples of deep learning and AI. You can use them also to solve things that we can't do yet. All right. So before the break, let me also, so that's it for the motivation, the introduction about AI. We'll now start more talking about the course and the lectures we'll have. So this course is Introduction to AI. I want to insist on the word introduction. We'll see many things. So the outline is like this. So today we have covered the introduction of about AI. We'll have a short lecture after the break on intelligent agents. And then from there on, we'll talk about many things. I will show you that in this way. The second lecture will be about problems. So we'll formalize problems as search problems, as things that an agent should do to achieve something, to achieve a goal. And we'll have 2 lectures on this topic. The first one will be strategy to solve these problems using search algorithms. Some of them you have already seen in the past. And in the following lectures, we'll have search problem extended to multiple agents acting together or against one another. Okay? And that will be the topic of the very first project. you will have to implement an agent which follows one of these algorithms. Then, so this is the first branch, I would say, of the content. Parallel to that, starting from the fourth week, we'll have a whole trunk of lectures about probabilistic reasoning. So usually this is the part that students don't like so much. They are much more comfortable with the one in blue than with the other. But really, probability theory will be necessary to implement anything in AI because you will not be able, you will have uncertainty and you need to account for this uncertainty to take optimal decisions. So I will need to introduce the whole framework again of probability theory. So we'll see that in the fourth lecture about quantifying uncertainty. Then we'll have a lecture on probabilistic reasoning in which we'll show what we call Bayesian network and inference problems and how to solve them, or some of them. Then we'll extend that to, in lecture 6, in problems where the agents evolves through time and has to take a sequence of actions through time. And so we'll need to anticipate and take into account the uncertainty. Here we'll see an important algorithm for AI and for you as engineers or computer scientists, which is called the Kalman filter. It's very important. And then we'll have a lecture on machine learning and neural network, which certainly will take at least 2 mornings to cover. And finally, we'll start merging all these concepts together. So in lecture 8, we'll have a lecture about making decisions in incomplete, uncertain, noisy environments. And then finally, we'll go a step further and we'll consider environments that we don't even know. So we'll have to acquire knowledge to understand them. We'll have to learn about them. So we'll combine what we've seen in machine learning in the framework of Markov decision process, and we'll arrive to the final lecture about reinforcement learning. And here you will see, by the end of this lecture, that we'll arrive to a very short algorithm that I can show you in one slide that you can use to implement an agent that can act in any environment, discover things about this environment, and then become optimal in this environment. So that's my mission. By the end of this course, you will have built autonomous agents that efficiently make decisions in fully informed, partially observable, and adversarial settings. It's fine if you don't understand these words yet. In 10 weeks from now, you will understand them. Your agents will be able to draw inferences in uncertain and unknown environments and optimize actions for arbitrary reward structures. So this is the main goals in terms of agents. However, what I also want you to get from this course is that we'll see many models, many algorithms that you can apply to a wide variety of AI problems. And so things, for example, that we'll see together in machine learning, you don't need to use them to implement agents to play something. You can also use them to, I don't know, solve medical tasks, for example, if that's something that interests you. Okay? So they will serve as the foundation for further study in any application area, from engineering and science to business and medicines that you want to explore. Okay, so the goals and the philosophy of the course will be to introduce you AI in a very broad way. So I will not focus on one thing only. I hope that you will obtain a good understanding of the whole landscape of AI, even though I will certainly focus on one or the other topic. That by the end of the course, you will be able also to write yourself from scratch some AI algorithms. The simplest, to be honest, but let's start with something. We will cover both well-established and state-of-the-art algorithms. So it's a mix of what we call good old-fashioned AI, of the type that we were teaching from the 60s to the end of the 2010s, I would say. So this thing you should know and understand that they exist. But I will also introduce newer materials from research that are really new. So everything that will be about deep learning falls into this category. I hope that also by the end of this course you will be able to understand some of the open questions we have. So this This is not a new field, but there are still many open questions that we have, and that I'm sure you will have, and that I will not be able to answer. Okay? It's a fact because we don't have the answer ourselves in the scientific community. And you should be comfortable with that. Okay? We know how to build cars, for example, since more than a century. We know how to build bridges. We've been doing that for tens of centuries now. Okay, that's a well understood problem. But when it comes to AI systems, we don't know yet exactly how to build these things. We have a good recipe so far, but certainly there are better things to do. Okay, so if you want to go further, also this is also to tell you that this is an intro to AI. This is the first of a long list of courses that you could follow if that's a topic that interests you, and that we offer at the university. So I think this is maybe the only one that you have access to in the bachelor program, but later on in your master program, there are plenty of other courses that you can follow on the topic of AI, foundations of data science, introduction to machine learning, deep learning, advanced machine learning system design, reinforcement learning, intelligent robotics, knowledge representation and reasoning, computer visions. All of them talk about AI and deep learning and so on. Okay? So also understand that I will not be able to cover everything in one course. We need 10 of them to cover them. Okay. So let me switch to something else. Okay. So today we still have one more lecture now after the break, but it will be much shorter, don't worry. Before the break, I want to go over the course syllabus, which is basically what we call in French the engagement pédagogique, the way the course is organized. So first of all, regarding the lectures, well, I will be giving the lectures and all of them. We'll have exercise sessions, which will be organized by myself, Jérôme, and a couple of student instructors. And you will also have programming projects, and this will be led by Arnaud. So if you have any questions, feel free to contact us, either directly during the course, during a break, or preferably by email to this address. Okay? When you send an email to this address, we all receive the emails that you send, and hopefully one of us will answer more or less quickly. There is also a Discord server that you can join. If you have questions, again, feel free to drop them on the channel. The materials, they are all available on GitHub. So I usually use GitHub for my courses to basically centralize all the materials. So the one for this course is available at this URL. So github.com/gloop/ the code for the course, and then introduction to AI. Okay, you will find the link also in the engagement pédagogique. And so all the main informations will be always put there. Okay, I'm not using eCampus or other things. I'm just using this. If there is really something important for you to know, I will send you an email. Okay. There you will find the slides for the theoretical lectures, both in HTML and in PDF. I would not advise you to print them all now. Usually I make small changes a few days before, if not the day before. So maybe wait until the day before in the evening if you want to print them. If you work on a tablet or on your laptop, of course you just download the day of the lecture. There are videos if you want to rewatch the course. So during COVID, I had to teach remotely. So all the videos that I did are available on YouTube. But to be honest, they are a bit old. So the content has evolved since then. So they are not up to date. They are also covering materials that I do not see any longer. So don't look at them as like some grand truths that you should believe. However, what I will do this year is that I will record everything on Unicast. This is what I'm doing now. And so you should have the lectures also available to you online on Unicast. Okay? The textbook. So usually you will have all the information directly in the slides. But sometimes the explanations that I'm giving are very sparse. Usually I talk more during the lecture than the content that you have on the slides. So you can take notes. If you want longer or alternative explanations, you can also just read the content in the textbook. So I'm following at least some of the chapters of this book, AI, a Modern Approach. It's not really modern anymore, but that's the title of the book. It's freely available online if you find your ways. But what is important also is that it covers both the theory and some exercises. At the end of each chapter, you will find suggestions for exercises, and usually the exercises that we ask during the exercise sessions or at the exam, they follow some of these suggestions. This course, my course, is also based on another course which is called Introduction to AI, but from UC Berkeley. So I really invite you to also consult the materials that are available there. You will recognize some things that I've reused. I'm not hiding it. It's not exactly the same in terms of content, but there is a lot of overlap. You will also find many exercise sessions, exams there if you follow this link. You will also see in my slide many of these cartoons. They are not made for my course at UGH, they were made for this course at Berkeley, but I'm reusing some of them. Voilà. Okay, the exercise sessions. So usually what we used to do in the past, until last year, was to have François, one of my researchers, to come and give you exercises, and he was solving them directly on the blackboard. We find that this is not very satisfactory. You don't learn so much by just copying what he's writing and what is anyway the solutions that we will be giving you. So there is no real added value in doing these exercise sessions anymore in this way. So what we want to try this year, and this is taking into account the feedback that we received in the previous year from you or your predecessors, is to still have exercise sessions, but in which you will solve them yourself, and will be several of us, myself included, passing by in the amphitheater and give you further explanations, help you to solve the problems, and so on and so forth. And certainly what we'll do is that we'll mix this with certainly also a bit of blackboard explanations to show you how to solve at least one of them, and then we'll go on and we try to solve all the others. So for this to work, of course, we expect your active participation. If you just come and wait for the answers, don't come, we'll provide them anyway. All the solutions will be given directly on GitHub. Okay, but for you to try to solve them yourself, which is what eventually you should be able to do if you want to succeed at the exam, well, this is the opportunity that you can use to practice this skill. Okay? Programming projects. So you will have two programming projects this year, or maybe three, depending on how we count. So the first one will be a tutorial which we'll do together in class next week. And what is common to all of these projects is that you will have projects in the environment of the game of Pac-Man, and the goal will be for you to build an agent, so a small program that controls Pac-Man to play the game. Okay? And so the very first project you will have to do next week is to write an agent to solve the problem of you have a maze like this in which there is no ghost, there is only food, one food, and you have to find it. Okay, easy. Next, in project 1, the one that will count for your grade, you will have to the second project will add back the ghosts, and you will still have to eat all the foods. So the ghosts will be adversarials, they will try to kill you, and you will have to account for that. Next, the second project, the ghosts will still be there, but since they are ghosts, they will be invisible. But you will have some kind of device to try to estimate the distance to Pac-Man. Of course, this device will be imprecise and noisy, so you will have to account for these measurements to try to guesstimate the position of the ghost, and then to still solve the game. Okay? Evaluation. So you will have a written exam that for 60% of the final grade, and then the programming projects for 40% of the grade. Project 0, which will be done in class, will not count for the grade. Project 1 and 2 will account for 20% of the final grade. Okay? Okay, the projects you will have to submit them on Gradescope, which is the interface that we use to centralize all the submissions. And we don't want to hide it, but students seem to be surprised by this before. All the projects are evaluated automatically. Okay, we are just running tests on your submission. We don't even open it sometimes. And if all the test passes, you will succeed. Okay? So you should realize that the projects are evaluated automatically on Gradescope. However, when you submit your project, only preliminary tests will be run, and you will see the results. And it's mainly for debugging purpose to see if you have included all the files, if at least we can run your Python program, but will not tell you if you pass or not. Okay? We'll have a second suite of tests that we'll actually use to assess the correctness and the efficiency of your solution. And these tests, we don't give them. Okay? That's a choice. Okay? Why do we do that? Because it's part of your job as a programmer to make sure that your program is correct. Okay? So it's part of the learning experience to also be to conceive and design the test that you should run to assess the correctness of your solution. And that's where you have to think, because you have to anticipate of all the corner cases that we may think about and that we will test. Okay? The efficiency of the code will also be taken into account, meaning that you may have an implementation which is correct, which gives the correct solution, but it may be so inefficient that it takes minutes or more to provide this solution. In this case, you will also be penalized for that. Okay, finally, the honor code for the project is that, of course, you are free to consult any resource that you want, meaning papers, books, online references, or even publicly available implementations for ideas that you may want to adapt and incorporate into your own project. And you can do so as long as you cite your references. Okay? However, you cannot use you may not base your project on someone else's implementation. Okay? We'll check for plagiarism if we discover that you've reused or adapted the implementation of someone else. And that happens often because we are a bit lazy and we keep the same projects every year, so it's very tempting to reuse the solutions from previous years. But we'll check. We have a huge pool of solutions, thousands of them, that we can against which we can double check your solution. So we'll check that. Okay. If we find it, okay, you will be sanctioned by a grade of 0, and that case of plagiarism will be reported to the faculty office. Okay. If we don't catch you, okay, I don't want to know. I know that happens. Okay, but if we catch you, that's the procedure. Okay. Also, you cannot use large language models like ChatGPT, Copilot, Cursor, all these things that I showed you myself are very helpful to implement the project. Okay? What really, of course, that, to be honest, that's very difficult for us to check that because it will produce randomized solutions. Very likely, two random solutions will be the same. But we want you to be able to not use, I mean, your mom can use that. This 8-year-old girl can use these tools. We want you, with this course and the others, to be able to build these systems. So you need to write, you need to be able to write the computer code behind this. Questions? Yeah.
Will we be provided with the exact scoring functions?
No.
For each of the, okay. Oh, that's, because you said it was a double metric, so like efficiency.
Yeah, that's for you to design.
Okay.
You know when I learned computer science back in too long ago, what we had to do was to send our project to the email of the assistant. That was it. And then he was doing all these tests. And even if one of them failed, like it can't compile or whatever, then it stopped.
We will be provided with the score or just the...
You will have a pass or fail information, meaning, okay, the preliminary test they passed, that's it.
Is it possible to mass submit?
To what?
To mass submit on the platform? I don't remember what was it.
Yeah, on CutScore, yeah, you can submit several times if that's your question.
Like many times.
Sure, but the goal is for you to do it locally. I mean, when you will have to implement one of these things for real, you will not have us behind you telling you if that's correct or not. Yeah. Yeah. Yeah, it's a group project. So I will tell you about that later on, but up to 3 students. Okay, so let's do a last break, and we resume at 11:05 or something. Oui, attends.